Okay class, so the purpose of this video is to help you with that third worksheet that we haven't gone over in class. And we'll get started right away. So we have this function given to us. This is a graph of f of x. It does have two endpoints, one starting at -3 and ending at x equals 8. And we're going to answer several questions about it. First of all, where are the critical points of f? Well, the critical points are going to happen any time that the derivative is 0 or undefined. And that happens in several places. I notice here at -2 there's a cusp looking thing, so that's definitely going to be so as we said earlier, at -2 we have a critical point right here. We're going to have another one here at 0 because this is a vertical tangent line. A lot of times people miss that one. It's not a common one to see. Now here at 1 we have another one. It's just kind of hard to see, but technically that line is supposed to flatten out. And then again at 3 we have a 0 derivative, and at 6 we have one more 0 derivative. So we have 2 places where the derivative is undefined and 3 places where the derivative is 0. So we would say that these critical points happen at -2, at 0, at 1, at 3, and at 6. Endpoints are not considered critical points, so even if right here at -3 it looks like the derivative should be 0, we're not going to include it because it is an endpoint. Next question is relative extrema, and what kind? Well, you can see that this is going to be a relative max, so let's go with local max. Local mins. Local max is going to be -2, so x equals -2. That's not an extrema, that's not an extrema, and then we have another one at 3. Local min, oh, we have one more. That's the endpoint right here. That's one that people typically forget. The actual y value is a little higher than the stuff before it, so we actually have one at 8 as well. For local min, we're going to have the endpoint because it is lower than the stuff around it, so -3. We're going to have 6. Whoops, I skipped one. -1. -1 and 6. Let me check if that's all. So we got one there, we got a -1, and then 6. Now for absolute max, we do have an absolute max that happens at 3. So the absolute max happens at 3, x equals 3. And then we have an absolute min, but in this case it happens in 2 places. So absolute min happens when x is -3 and also -1. Absolute extrema, whoops, I guess I should have put that one here. Kind of answered 2 questions in one. This one was just supposed to be relative, and this one's the absolute. All right, inflection points. Now, inflection points are where concavity changes sign, changes. So where does the concavity change? Well, I can tell here that we're concave up, and while it's tempting to pick -2 as an inflection point, on the right side the concavity is still up, so there was really no concavity change, so we can't include -2. But if you notice here, we're going to switch from up to down for just a little bit here, so x equals 0 is going to be an inflection point, and then it switches right back up to 1 at, looks like 1, so it's concave up and then down and then up, and right about 2 it looks like it switches back to down. So I'm going to include that guy, and around, I would say 4.5, looks like it switches right back up to up. So for my inflection points, I would say that they are x equals 0, 1, 2, 4.5, and that one is a little bit debatable. Some of you might have gone with 4 or 3 or 5. That's fine. Anything in that range will work. So that's our inflection points. All right, now let's take this graph and make it a first derivative graph. In the first derivative graph, we're assuming that we have never seen the original. This is just the first derivative. And now we're asked to find the critical points. Remember, the critical points are where the derivative equals 0 or undefined. So let's take a look. Is there any place where the y values of this graph are 0? And there is. There are 3. Here, at -2, at 0, and at 6. So those are our critical points. Okay. Next, the relative extrema and what kind? Well, to find the relative extrema, I often find it useful to make a chart. So what I do is I make a nice horizontal line and I put my derivative up here, regular graph here. I put my critical points on it. So I have -2, I have 0, and I have 6. Okay? So I have those 3 points. And I'm going to just take a look at the graph and determine whether the derivative is positive or negative. Since this is the derivative of f, we are not looking for direction, we're simply looking for the actual y values. Each of these values represent the derivative. So before 2, you notice the y values, I'm not going to look at the direction, I'm just going to look at the y values. They are negative. So the implication there is that the function is decreasing. Then, after the -2, all of these y values are still negative. They're below the x-axis. So my function should still be decreasing. Now afterwards, the y values become positive all the way until 6. So I have a plus. Again, I'm not looking at direction, I'm looking at the y values. And after 6, they continue to be positive. So that's increasing. So this function was decreasing until 0 and then continued to increase after that. But something that's different about this function is that it has endpoints. And we haven't really dealt with that yet. So I'm going to go ahead and erase these arrows. And in place of these arrows, I'm going to put brackets to show that we have endpoints. Okay, and that endpoint is at -3 and at +8. So what's going to happen is the following. If I sort of trace this function, let me do it in a different color. If I trace this function, I know it starts somewhere. I'm not really sure where, but I know it starts at x equals -3 and it decreases because my derivative is negative. So it goes down. And then at 2, it kind of flattens out because the derivative is 0, but it continues to go down until you get to 0. At 0, it switches to increasing because the derivative is positive. Now again at 6, it kind of flattens out for a little bit, but it continues to go up until I get to 8. So here's something really, really important. You can tell that x equals 0 is going to be not only a local, but an absolute min, for sure. So x equals 0 will be a relative or local min, and it will be an absolute min as well. Okay, but a lot of times people forget about the endpoints. Because we have endpoints, you have to look at the behavior right after the endpoint or right before the endpoint to determine whether it's a max or min. In this case, although we don't have a graph, but we do know that it's decreasing, you can tell that this endpoint is going to be a local max. Okay, so x equal to -3, it's a local max. And on the other end of this endpoint, because the function leading up to it was going up, it ends at the highest point here at x equals 8. So that makes it so that x equals -3, and I'm going to squeeze in 8 as well here, are both local maxes. Okay, -3 and 8 are local maxes. But the last thing, and this one is a question, I would make it a level 4. It's one of those making inferences beyond what's taught. So the last thing I want to mention is for sure x equals 0 is our absolute min. But if you think about it, these are relative maxes. How can we tell which one is higher so that we can determine if it's an absolute max? Well, in this particular graph, you can tell that you are decreasing for a while, but you're only decreasing for about 3 units, from -3 to 0. You're decreasing for those units. and then you begin to increase, but you increase for a really long time. You increase from 0 all the way to 8. So what that tells you, it's basically like saying, hey, the function takes 3 steps down and then 8 steps up. So clearly, if you go down 3 steps and then up 8 steps, you're going to end up higher than where you started. So think about it as steps, going down 3, going up 8. Well, what that's going to mean is that we went up longer than we went down. So we have an absolute max at x equals 8. Okay. And lastly, inflection points. Inflection points in the first derivative are the turning point. So it's anywhere the function or the first derivative changes direction. So let's follow along. We were going up and now down. That makes -2 an inflection point. We're going down and now up. So that makes -1 an inflection point. We're going up, 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 and we switch directions here at 3. Inflection point, down, 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 switch directions at 6. And so we have -2, -1, 3, and 6 are all inflection points. Okay. All right, let's switch now and make this the graph of the second derivative. So this is the graph of the second derivative. Determine inflection points. Well, inflection points are anywhere the second derivative switches from negative to positive. So you can tell that this second derivative is negative before 0 and positive after. It doesn't quite cross over here at 6. So really the only inflection point is x equals 0. I crossed this one out in your notes or in your worksheet because after years and years of giving this worksheet out, we've never been able to determine extrema from a second derivative. It just came with the original worksheet where I got this from, but I think it might have been a typo, and I've even asked people from AP trainings and they have not been able to solve it, so that's why I crossed that one out. State intervals of concavity. Well, concave up is going to be where the second derivative is positive and down where it's negative. You just got to be careful every time it touches 0 not to include that. So let's see, concave, let's start with down. It's going to be from -3, and I'll be careful to use parentheses because concavity is in an open interval, to -2, and from -2 to 0. And concave up is going to be from 0 to 6, and then again from 6 to 8. And that's it. Let me know if you have any questions. I hope this was useful. Please make sure you finish this and then the other review worksheet so we can have a good discussion on Monday. Have a good weekend.